Hi, this is Dr. Remenacker. In this particular video, we're going to focus on rational exponents, not rational functions, but rational exponents. In mathematics, the word rational basically boils down to meaning a fraction. So what we're going to be working with in this particular section is how do you handle exponents in variables and how do you handle fractioned exponents. This is really important that you get down because this is going to be something that's going to come up time and time again, basically on almost a daily basis as we're working through calculus. So this is a very important set of ideas to have down because you're not going to get far in your calculus sequence without this. Okay, there are four basic properties we first want to take a look at. And the way you'll see them displayed in a book or publication is like what I have listed here. And people will look at that and say, yeah, well, that doesn't mean much to me. An example of this would be something like, suppose you have x squared times x cubed. And the question is, well, gosh, what does this equal? And people are trying to figure out, do I add the exponents? Do I multiply the exponents? What do I do with them? Well, according to the property that you're given here, what you're going to want to do is add the exponents. Well, that's all fine, but why would you add the exponents and not multiply them? Let's turn back to our example on the right here. The x squared is basically x times x, and the x cubed is x times x times x. And if you simplify this, this is actually x to the fifth power. In order to get that x to the fifth power, you don't multiply the 2 times the 3, but you actually add the 2 plus the 3. So as you can see here, this property is based on the idea illustrated in this example. Very honestly, I don't memorize these things all that carefully. I turn back to this example I've just given you here when I have two variables I'm multiplying together and oh man, what do I do with the exponents? Do I add them? Do I multiply them? If you want to go this route, it works or it's worked well for me. One of the things to be careful of is if you have x squared times x squared, well, that gives you x times x times x times x equals x to the fourth. But in this case, it's not clear if you added the twos or if you multiplied the twos. So if you're going to fall back on an example as a way of deriving the um, rule, be careful. Use 2 and 3, not 2 and 2, because it's not real clear when you use 2 and 2 if you took 2 times 2 to get 4 or if you added 2 plus 2 to get 4. In this second example, or basic property here, notice if you have one variable divided by another variable, you subtract the exponents. An example of this would be something like x to the fifth divided by x squared. Well, this could be written as x to the fifth with 5 x's in the numerator and x squared with 2 x's in the denominator. And what you could do is you could just cancel out a couple of these, and that will then produce x to the third. And as you can see, if you come back to our original setup here, 5 minus 2 will give you x cubed. The subtracting is based on the idea of which you can see over here where with the blue lines we canceled out. We're taking away. So the taking away is the subtracting, where we're going to subtract whatever's in the denominator from whatever's in the numerator. The third property of the four that are critical to be familiar with is this one. And an example of this would be something like x squared cubed. And as in the earlier example, I'm going to be careful to use 2 and 3, not 2 and 2. Well, recall that if you cube x squared, that's the same thing as taking x squared times x squared times x squared. Cubing means you multiply it together 3 times. Okay, well, we can write this out or expand this a bit. The first x squared is x times x. The second x squared is x times x. The third x squared is x times x, which is going to give us x to the sixth power. With the 2 and the 3, the most reasonable way to get the 6 is by multiplying them together. Okay, so this is what is illustrated here by the actual property that you're given. You take the two exponents and you multiply them together, just like we saw in the example. The fourth of the properties is essentially a definition. It just says, hey, if we have something like x to the negative 3, that's the same thing as 1 over x cubed. Okay, so what you're going to wind up with here is 1 over x cubed. If you want to draw a parallel with this in the last problem, you could write x to the 0 over x cubed, which is really x to the 0 is 1 over x cubed, like that. Okay, so we could write it like that, and that would work out fine. Using the property that we just looked at, number 2 above, remember, if you have a situation where in the numerator you have x to some power divided by a denominator with x to some other power, you take the exponents and you subtract them. So this x to the 0 over x cubed could really be written as x to the 0 minus 3, which will give you x to the negative 3. So there are a variety of ways to look at this. But remember that anytime you have a negative and an exponent, that means you want to do its reciprocal. The negative in the exponent, this is really important. The negative in the exponent does not mean it's a square root. People will sometimes make that assumption. That is not accurate. We'll take a look at what a square root looks like here in just a moment. In fact, let's take a look at now as we evaluate some of these different problems. Okay, so in the first case here, we have x to the 1/3. Now be careful. It is not a negative. This is not equal to 1 over x cubed. That's not what this is. That's not what it's saying. The negative is what indicates we have a reciprocal. What this indicates here is that we have an x that we're going to raise to the first power, and then we're going to apply the third root. Okay, so what does that mean? We're going to have x to the first power and apply the third root. Well, x to the 1 is just x. Oh, this is just the cube root of x. One of the things that is sometimes useful for people to keep in mind is the root 3 is in the denominator of any fractional exponent. And I always make the comment that, if you're looking for the roots of a tree, where are they, above ground or below ground? Well, they're obviously below ground. Same thing here when you have an exponent that's rational, the roots are below. Let's take a look at and apply this in a second example. We have x to the 5/4. The 5 is an exponent like that. The 4 is in the denominator, so it is a root. This is x, okay, to the 5/4 power rewritten with a root. Let's take a look at the third one here. I'm going to take this in 2 steps. The first step being to deal with the negative. This really says 1 over x to the 3/2. The negative says we're going to do the reciprocal. Now, the next step is going to be, I'm going to write down my numerator just as it is. And just like we did in the problems above, 3 is a power, 2 is a root. So we have x to the 3rd, and we're going to apply the second root. You may not have seen that notation, and the reason is because the second root is the square root, and it's understood to be a 2 unless there's some other number there. So anytime you write a square root, that square root automatically includes the 2. Let's take a look at something like this. In this case, we have x to the negative 1/5. As with the problem we just did, I'm first going to do the reciprocal part, which is going to give me x to the 1/5 power. Now, I'm just going to focus on the denominator. I'm going to have my x. The exponent is the numerator of that fraction. It's a 1. And the root is a 5. So this is really x to the 1/5 power in the denominator, or the 5th root of x. One direction you wind up going is rewriting a rational exponent using the root sign. What we will often wind up doing in calculus as well is we're going to have some root, as you see on the right-hand side, and then we're going to need to convert that to a rational exponent. So let's work things in the other direction. In this case here, we have a 4th root and an exponent on the x of 1. So we're going to have a 1 and a 4th root. Okay, so there's that. In the second case, we're going to have our x. The exponent is a 5 with the square root. We talked about this. A square root is understood to be a root of 2. So this is going to be x to the 5/2. Okay, now this one is going to be a 2-step deal. The first step in it is going to be to rewrite it as x to the, well, it's squared and a root of 3, like that. So it's 1 over x to the 2/3 power. Then, to get this back up on the top line, I'm going to indicate that it really came from a reciprocal and introduce the negative sign. So it's going to be x to the negative 2/3. The last of these 4 examples, I'm going to rewrite this. We have x to the 4th power, and we have a root, roots go in the denominator, of 7, and that has that. Being able to work fluidly in either direction is going to be very important to your success in this course. If you cannot write down the function that you're working with, you can't get any further. You'll be stuck at the very first step, literally, of many problems if you cannot do these. Be sure that you practice enough of these to become fluent in this. Okay, so let's revisit the idea of computing domains. The first of the 2 examples that we're going to look at here is y equals the 6th root of 3x minus 9. Now remember, if you have an even root, this means that the discriminant must be greater than or equal to 0. That means this 3x minus 9 has to be greater than or equal to, it's okay to take the square root, the 6th root of 0. It's 0. So equal to 0 is fine. It just has to be 0 or bigger. So this is going to give us that this 3x has to be greater than or equal to 9. X has to be greater than or equal to 3. Okay, at this point now, we know that x has to be greater than or equal to 3, but we need to list our domain in set notation. One way to do this is to say that x is the set of values that go from 3 to infinity. Now remember, the parentheses mean that you cannot include that particular value. On the right side, it makes sense because you never get to infinity. But on the left side, are we allowed to include the 3? Well, if you take a look at our results over here, it says x is equal to 3 or bigger than 3, which indicates yes, we can include the 3, which means I need to change this notation here. This is not going to be a parentheses to indicate that we can include the 3. We're going to use a bracket. You only use this bracket if your inequality, over here on the right-hand side, is something like greater than or equal to or less than or equal to. In the second problem here, we have a square root, which means that this 2x minus 10 once again has to be greater than or equal to 0, which will give us that the 2x has to be greater than or equal to 10. Dividing by 2, x has to be greater than or equal to 5. So to identify the domain in this case, it's going to be the set of x values such that we can include the 5, so I'll use a bracket, going on from there to infinity, and we never get to infinity, so that's why we use a parentheses there. Now, there is a third problem here I want to talk about, and that's the case. Suppose you have something like y equals the cube root of 4x minus 7. If you're taking a cube root, in other words, an odd-powered root, then the discriminant, the stuff inside, can be greater than 0. It can equal 0, but here comes the new one. If it's an odd root, it can be negative as well. Remember, if you take a negative 2 and you raise it to the third power, you get negative 8. So if you're working with odd numbered roots, negatives are just fine. Well, in this case, that means then that this 4x minus 7 can be greater than 0. The 4x minus 7 can be equal to 0. And the 4x minus 7, here's the new one, can be less than 0. It can be any of them, which essentially boils down to x can be any number you want it to be here. So in this case, the domain would be the set of x such that x is an element of the real numbers. The real numbers is indicated with a capital R with 2 lines on the back of the R. Let's move on from here. Let's take a look at a situation like this one where you're asked to compute the domain. In this case, we're going to first look at the numerator and ask ourselves, are there any values of x that'll cause a problem in the numerator? And the answer is no. If x is negative, it's fine. You can have a negative numerator. If x is 0, that's fine. 7's a good numerator. And if x is positive, you're going to get positive numbers, which are fine in the numerator. So the numerator has no restrictions. This denominator we got to be careful of because this cannot equal 0. As we've discussed in earlier videos, you cannot have 0 in a denominator, which means then that we now need to solve this as this 2x plus 8 cannot equal 0, which means the 2x cannot equal 8, which means that the x cannot equal 4. If you draw this on a number line, and here's 4, 4 is the only number we're not allowed to include. Okay, so that means that we can include everything to the left of 4, and we include everything to the right of 4. Okay, so how do we explain that using our set notation? Well, the way that we're going to define our domain over here on the left-hand side is x is going to be an element of, and I'm going to break this up into 2 pieces because as you can see on our number line, it's broken up into 2 pieces. The left-hand side starts at negative infinity and it goes all the way over to 4. Now you've got to be careful because we can't include the 4, so we're going to use a parentheses, not a bracket. Along with this, united with this, we can start at 4, but we can't include 4 and go all the way over to positive infinity. So for this example here with this rational function, the domain is the set of all x from negative infinity to negative 4, or to positive 4, not including the 4, along with 4 to infinity, not including the 4. So this gives us the domain for this particular rational function. A situation that we're going to commonly or look at a number of times is that of supply and demand. Okay, demand is contingent on price. So what's going to wind up happening is we're going to have our price over here. The price depends, okay, and the number of units is going to be here. And remember, the price is going to control the demand. And as the price goes higher, so as we get bigger numbers in price, the demand goes down. So what's going to happen is when the price is way up here, you don't have very many sold. As the price starts to come down, more people are interested, and continuing to come down on the y-axis, more and more units, which are the x-axis, are going to be sold. Our demand function is going to end up typically being a decreasing function. Decreasing because as the price drops, the number of units go up. So this is going to be our demand function. This is commonly what will happen. On the flip side, we're going to have a supply function. When the price is low, the producer doesn't want to make very many of them because they're not making much money on it. But as the price increases, the number of units they're willing to provide goes up and up and up. So there's a direct relationship between price and the number of units that the producer is willing to supply. Now, one of the neat things about a capitalistic form of enterprise is that you get the vote on what price you're willing to pay for things. Really? I didn't get the vote on it. You do by buying it or not buying it, which then forces the producer into considering, gosh, I'm not selling as many of these as I wanted. I need to reduce the price. Okay, so you do have control over the price of things. If it's higher than what you want to pay for it, you just don't buy it. Where the demand and the supply function intersect, right there, is what's called the equilibrium price. This is an ideal price in that it provides the most units possible available at the lowest price possible, which really works out well for consumers and producers both. The producers get to make as many of them as they can, and the consumers get to buy them at as cheap of a price as possible. And there are a number of them out there. It's not just one or two. Okay, well, it depends on where the equilibrium point lands. Okay, but this equilibrium price ensures that both the demand side of the equation and the supply side of the equation have a say in what the price is going to be and how many are going to be available. Okay, with this in mind as a general idea, let's take a look at a specific example. In this case, you're asked to compute the equilibrium point or the equilibrium price when you have a demand function that's defined for you right here, and when you have the supply function right there. When you graph these, let's see what color, I used. Your demand function is a line. It's decreasing and it starts at 7 and it's just a line that goes down like this. This is your demand. The supply function, which we plotted in yellow and will continue to plot in yellow, is a square root and it's going to behave something like this. So here is your supply. A real fair question. You're going to be asked this on quizzes and tests and all over the place because in the real world, you've got to know where this point is. This is an important point. Compute the equilibrium point. Remember, the equilibrium point occurs where demand and supply intersect. By intersecting, that means that the demand is equal to the supply. This is a great place to be in production because the number of units you make is the exact number of units people want to buy. You don't have stuff left over. And on the other side of the coin, you're not missing out on sales because, oh, rats, if I would have sold an extra or made an extra 50,000, I could have sold those too. Okay, so how do we solve this algebraically? Well, you take your demand function, which is the 7 minus the Q, and you set this equal to your supply function, which is going to be 2 times the square root of Q plus 1. Now, I could have chosen an easier supply function, just made it another linear function, and that'd be real easy to solve. But part of the purpose of this particular problem is to get you warmed up on your algebra. Without your algebra skills being in good shape, calculus is just not going to go well for you. Okay, we need to solve for Q. Well, the first thing we need to do in solving for Q is to get rid of that square root. To get rid of the square root, what I'm going to do is I'm going to take both sides and square them. When I square each side, squaring the left side, be really careful. A lot of people put down 49 plus Q squared. That's not right, okay? You cannot distribute that exponent of 2 like you would 3 times it. What that squaring means is you have 7 minus Q times 7 minus Q. On the right-hand side, we're going to have 2 times the square root of Q plus 1 times 2 times the square root of this Q plus 1. All right, so we can FOIL out on the left side. We're going to have 7 times 7 is 49. So here are the first terms. The outer two terms are going to give me a minus 7Q. The inner two are going to give me a minus 7Q, so that's going to be minus 14Q. Then I'm going to do the last two terms. A negative times a negative is going to be a plus Q squared equals. On the right-hand side, I'm going to have the 2 times the 2. Remember, we have 4 separate things being multiplied together here. We have 2 times the square root times 2 times the square root. So I can switch the order around. I can rewrite this as 2 times the square root of Q plus 1 times the square root of Q plus 1. And that's going to give me 4 times, well, the square root times the square root is going to give us Q plus 1. Okay, so this is going to give us our Q squared minus 14Q plus 49 on the left side. Notice I just took and I got things in order from the highest exponent to the lowest exponent. Then I'm going to distribute this 4, which is going to give us 4Q plus 4. Move everything over to the left-hand side is going to give us Q squared minus 18Q plus 45. We have to subtract 4 equals 0. This will factor. This factors into Q minus 15 times Q minus 3 equals 0. Okay, well, that gives me 2 possible solutions. One of the solutions is going to be Q equals 15 units. The other solution is going to be Q is equal to 3 units. One of the things we need to be careful here is Right up here at the start of the problem, up at the top of the screen now, the first thing we did was we squared. When you square, be aware that you can introduce extraneous roots. Squaring can introduce extraneous roots or can create extraneous roots. Okay, so you got to be careful of that. Extraneous means extra ones that don't really work. So what I need to do now is I need to check and see if the q equals 15 and the q equals 3 really work. By really work, that means if I take my 7 minus q equals 2 times the square root of q plus 1, does it work for one, both, or neither of these values of q? Well, the first thing let's try is q equals 15. When we do that, we're going to get 7 minus 15 is equal to 2 times the square root of 15 plus 1. This is going to give us a negative 8 equals 15 plus 1 is 16, square root is 4. Negative 8 is not equal to 8. This root is extraneous. Okay, so we can't use this one. Now we need to check q equals 3. Substituting that into our original equation, we have 7 minus 3 equals 2 times 3 plus 1. On the left side, 7 minus 3 is 4. On the right side, 3 plus 1 is 4. The square root of that is 2. So we have 2 times 2 is 4. This works. This is our solution. Okay, now what we want to be careful to note here is that this is q equals 3. Our solution here is q equals 3. So when I bring it back up and I consider now my equilibrium point, my q is going to be 3, and I need to compute then the price. To get the price, what we need to do is to substitute this value for q into either of the two equations. It doesn't matter which equation it is. If we substitute it into the q, or the 7 minus q, that's going to be 7 minus 3 is 4. If we substitute it into the 2 times the square root of q plus 1, that's going to be 2 times the square root of 3 plus 1. So that's going to be 2 times 2 is 4. Either way, we wind up with 4 units, or I'm sorry, a price of 4. So the price, remember, is going to be on the vertical axis. The quantity, or the number of units, is always going to be on the horizontal axis. And with that, that takes care of this problem where you're asked to compute an equilibrium point. Problems like this are very common on quizzes, tests, and final exams, all three, because this is a very important idea to have in mind.